Hi, my name is Car. I'm a third year psych student. And just like a lot of people that have done psych at University of Groningen, I struggled a lot with my statistics 1B exam. It took me a bunch of tries, but I ended up passing with a 7. But it took me so much time and so much effort and that sort of thing. And I figured since I passed and I kind of have a okay grasp at it, I would just make a video, or maybe more videos. I don't know how long this will take, going over how I learned for stats 1B and basically how I interpret everything, and just go over everything in baby steps. Some of you guys may have seen my summaries go around for stats 1A and 1B, where I basically drew the entire summary, which was one of the ways that I ended up also passing eventually, because I just started visualizing stuff. So I don't know if this is going to be a series or just one very long video. We will have to see. Anyway, let's get into it. So we're going to start with basically doing a mini recap of stats 1A, and only like the important stuff that we're going to be using in stats 1B. So in stats 1A, we went over descriptive data. And the main things that we learned there is how to get our mean, how to get our standard deviation, how to see, like, is it a normal distribution, and how to get your z-scores. These are the basics. I'm going to assume that you know what these are and that sort of thing. If you don't, I will link my drawn summary for 1A somewhere, because I think that it will give you a proper understanding of what these are, because I generally see them as building blocks. Because just saying we have this sample and this is the mean of that sample says very little. We can't really make any conclusions out of it. We don't really know what to do with it. It's just a number. What do we do now? Well, that is where we go into stats 1B, which is statistical inference. When I first started doing statistical inference, I didn't really have a firm grasp of what that even means. I didn't really have a clear idea when I heard statistical inference what they want from us and that sort of thing. So I looked it up, and the way that I kind of see it and the way that I interpret it is basically based on the summary, like the summary of this and our sample, we can make an educated guess on the true population given our sample. So that is what statistical inference is, because if you have a whole population, and if in some magical world we could interview and research everyone in that population, we would know the true population, mean, and standard deviation. When we know the true population, we use the Greek lettering, which is almost impossible because we can almost never do the entire population. It is impossible. There's too many people. So instead of doing that, we grab a sample. And instead, because we don't know the entire population, we now have a mean, which we depict with X bar, or we have a standard deviation, which we depict by S. And with inference, we basically do some calculations based on the sample, and we make an inference. We make an inference based on that sample about the true population. That is the basics of why we do statistical inference. It is because we can't research everyone. We take a small sample, and based on our calculations, we can make an educated guess or an educated assumption about the true populations. In my head, I also see that there are two main big families of inference. So statistical inference. Statistical inference. There's a bunch of different ways to make conclusions about the population mean and the population everything and that sort of thing. But a huge chunk of Stats 1b will go over two main families, which is the significance test and the confidence interval. I will go over the different things as well that are also included in 1b, including like Bayesians and that sort of stuff. But a huge part of 1b is just these two families. They will differ a little bit, and you will use different subcategories of each in different scenarios. But on a basic level, you basically have the significance test family and you have the confidence interval family. And that is kind of how I visualize it. Anyway, that is the basics. So now let's get started with the very basic version of the significance test. Alright, so the significance test. The significance test, the most basic version of that is the one sample Z procedure. So the building blocks that we will need is the mean of our sample, the standard deviation, the sample size, our null hypothesis, and an alpha level. I'm going to go over each one of those. So at least the ones that are of import. When it comes to the significance test, what we have is basically we have our null hypothesis. Null hypothesis. The null hypothesis is basically an assumption we have made about the true population mean. And we are going to test that versus an alternative hypothesis. Alternative. Yep. And what we basically say is like, well, we have our first hypothesis, which is mu is something. And we look at our alternative hypothesis, which is mu isn't that, or mu is smaller than that, or our mean is larger than that. It's basically just looking at this and saying no. The entire goal of the significance test is basically just disproving the null hypothesis. When we do our entire test, the only result we can get out of it is either we accept or we reject. When we reject the null hypothesis, we do not immediately accept this one. Like, we don't say, oh, the alternative hypothesis is correct. We just say the null hypothesis is likely not correct. So, yeah, that is kind of like the basic of it. So let's look at the basic formula for that. Is we look at our Z, or at least we want to find our Z. And we use our building blocks. So that is our mean of our sample minus our null hypothesis divided by our standard deviation divided by the square root of our sample. So that is the basics. And the result we get out of that, we look up in our table A, which is given during the exam. You can just look it up in here. I'm going to walk you through it with examples and everything, so don't worry. But you look that up. Whatever you get out of that table A is now your p-score. What do we do with that p-score? Well, as we could see in our building blocks here, we have our level alpha. Our alpha level is basically our cutoff point. we have our standard deviation, like our normal distribution, and we have our cutoff point at like 5% over here. If we say that our mu is over here, but we see it in our sample, it's right there, we're going to probably be like, well, we're going to assume that this is incorrect because it's so, like, our sample mean is so far away from the null hypothesis sample mean. It probably isn't this. It probably isn't the mu. So we're going to reject the mu. It's probably bigger, smaller, or just isn't this one. That is the basic. So we choose that cutoff point. Let's remove this. What we do with our p-score is basically just we compare the score, the p-score, to our alpha level. If our p-score is smaller than our alpha level, which means that in our little distribution we had our cutoff point here, but we found that our p-score is right here, so even more extreme than our alpha, we reject the null. That is the conclusion we get to. It just means that no, there's a high likelihood that given our sample size that the null hypothesis is incorrect, or there is a better way of looking at it. So let's look at an example of IQ. So we know that generally speaking, we have a null of 100 because usually we say that the IQ in the population is 100 with a standard deviation of 15. And then we grabbed a sample of 25 people. And when we tested them and we looked at their scores, we actually found a sample mean of 125, which is quite a bit higher than that mu of 100. So now we have our null hypothesis is that mu is 100. The true population mean is 100 versus our alternative would be that it is more than 100. Then we're going to do the testing. And also, let's say that our cutoff point is at 0.05, because that is most of the time, that is what we look at. There are smaller ones, but generally it's 0.05. Okay, so now we're going to put those numbers into our nifty little formula, which was z is x bar minus mu divided by significant, like the standard deviation, and n. Well, that is now 125 minus 100 divided by 15 divided by the square root of 25. The result of that is an 8.333, which is really high. That is now our z-score. Now we look at our table A, and you always look at D's and stuff. You basically just look up everything in there, and we see that it's very, very, very small because it is positive. Like, this is the all of the positive numbers you can get out of your z-score, so it's always 1 minus whatever score, which means that we get to a p-score of smaller than 0.001, which is very small. Well, then we're going to compare this p-score of 0.0001 to our alpha level of 0.05, which means that our p-score is way smaller than our alphas. Thus, we are going to reject our null. We assume that the true population mean isn't 100, it is likely bigger given our formula. However, this is a very extreme example, of course, because we found a way, way higher number. Let's do it again. But this time, we found that the population is only a little bit smarter. So everything is the same other than that. So (0.05). Let's do it again. So we have our nifty formula of x bar minus mu divided by standard deviation square root of n. That, and now we're going to plug in our new numbers. 101 minus 100 divided by the 15 divided by the square root of 25. And now our result is 0.333. Well, then we're going to look at our table again. First we found the 0.3 over here and the 0.3 over here. Then we're going to look at what that corresponds to. And that is 0.6293. So our z is 0.6293. That is our p-value. Our p-value is now 0.6293. That is bigger than our alpha level of 0.05, which means that we accept the null. We're going to assume that the sample was so similar to our assumed true population mean, therefore we're going to just accept it. There are some things within significance tests that is very popular to do. Like, it's a popular test to do because it is very eye-catching to say, ooh, we found a significant result. However, it doesn't really tell us a whole bunch. There's also just very easy ways of manipulating data to make it look very significant. And a lot of, like, basically hacking. P-hacking is what it's called. So generally, if you want to be more honest, you would do a confidence interval, which gives us more realistic numbers than our significance test. But we're not here to criticize the research world. For now, we just need to know that this is the basics of significance test. This is literally, from here on out, we're going to modify small things within this main test, but it all boils down to this formula. Anyway, that's all for the basics of the significance test, so let's move on to the basics of the confidence interval. Alright, so now let's move on to the confidence interval. So the building blocks that we're going to need for this one is, once again, the sample mean, the standard deviation, a confidence level, and a sample size. Because we always need a sample size. And basically what we get when we do a confidence interval is we can say with X amount of confidence that the true population mean will fall between X and Y. That is all we say. And it is a way more honest way of looking at data. You give your readers a certain level of confidence where the true population mean will fall. It is, in my opinion, a better way of doing data collection than the significance test. Anyway, that is the basics. So let's look at a little example of how we use that in practice. Basically, every single one of our confidence intervals will look like this. Mean plus minus m. What does m stand for? M is the margin of error. It is basically the interval in between x and our lower bound and our upper bound. That is our margin of error. How do we get our margin of error? Well, that will fluctuate depending on which type of confidence interval we use, obviously. But generally for the one sample z procedure, it is plus minus z times standard deviation divided by the root of n. This here is our standard error. And this is determined by what level of confidence we have. So for example, if we want to have a 95% confidence, we are going to look at our table. I suggest looking at your D table instead of your A table, because down here, there is just a Z like row. So you just have to look 95%. So you can see that our Z for a 95% confidence interval would be 1.96. Generally, like the 95% confidence interval is the most popular one, so most of our tests will be around that. So let's do an example of that. Let's go back to our very smart people that had a mean score in our sample of an IQ of 125, which is pretty high, but you know, whatever. Then we're gonna have our 15 standard deviation. We want to have a 95% confidence interval. So if we then check here again, we see that's 1.96. And we have a sample of 25 people. So now we have our formula is z times, so let's plug it in, 125 plus slash minus 1.96 times 15 divided by the square root of 25. There we go. Then we're going to calculate that, and we see that this ends up being 5.88. Well, we grab our mean, minus 5.88, and plus 5.88, which would give us 19.12 and 130.88. So we can say with 95% confidence that the true population mean will be 119.12 and 30.88. So with 95% confidence, we can say it falls in between here. Obviously, there's the 5% that it will be smaller or higher, but with our sample, this is what we conclude. And what do we really want to do? What is our goal? Well, we want to have a relatively narrow margin of error with as high as confidence as possible. Why do we want it to be narrow? Well, if we have a confidence interval that is so large, then it becomes insignificant. Because if we say with 95% confidence, we can say it falls between 50 and 100. That's a big margin, and it doesn't really tell us much. So how do we narrow down that margin of error? Well, we can do that in a few ways. So we can either decrease our confidence level. So now we can, for example, say with 80% confidence, which would narrow it down, but it would also increase, now we have a 20% chance that it doesn't fall in between these two spots, right? So it reduces our confidence, but it will make it more narrow and therefore more meaningful. We can also just increase n, or we can decrease our significance, our standard deviation, but that's very difficult. We don't really know how to do that. So those are the ways to narrow down your confidence level. I mean, your margin of error. Now, let's say that we have a margin of error that we want to have, let's say we want to have a margin of error of 15. Or maybe it's a little bit big. Let's say margin of error of 10. And we want to have 95% confidence. So that would be 1.96. And we also know our standard deviation is still 15. How many people do we need to get this? We can redo our calculations to get our n, which would then be 1.96 times 15 divided by 10 squared. If we do this, let's look that up on my calculator real quick. So 1.96 times 15 divided by 10 squared would be a 8.6436. Since we cannot have partial people, we always round this up. So we would have we would need a minimum of 9 people in our in this test to get to that margin of error. That's kind of like the basic way of going about this. This is just a formula you kind of just need to memorize. I think that the confidence interval is a lot easier than the significance test because it just has less steps and you get a more honest answer. But yeah, that is the most basic version of the confidence interval, and we're gonna go into like more elaborate versions of that. But now you at least have the basics for both the significance test and for the confidence interval. Well, those are the basics. So let's add a second sample. Because I know that in the lectures and stuff, they first go into T procedures and that sort of thing. I find it more understandable if you first look at the two sample Z, because at least the way that I interpret it, it's basically every T procedure and stuff is a deviation from the most basic sample, which is the Z. So we're first going to go over the two sample Z, and then later on we're going to go back and actually look at the T procedure. So now we have a new formula that is slightly different for the two sample. So why is it now suddenly especially for the standard deviation, the significance test, we see that there is x1 minus x2, and there is no mu here anymore. Why is that? Well, it's because the mu basically in the two sample, they basically say that mu1 and mu2 are the same thing, aka the difference is 0. Because if you were to do mu1 minus mu2, it would be 0. Well, something minus 0 is nothing, so we ignore it. Technically, the full formula would be this minus, like this, minus delta. And delta is mu0 minus like the two mu's, so 1 and 2. But because it's 0, we just completely leave it out. So why do we have all of this? Why is it so complicated over here? So as we can see in the, let's see, the one sample, we had this, the square root of n and the regular standard deviation. Well, now we have two standard deviations and we have two n's. How do we get that done properly? Well, if you have the ST42, we're gonna pull that square up. But we still need like a regular standard deviation. So what we do is we square that one because the square and the root equal each other out. So then we can just use regular n, we don't need to square it anymore, plus the standard deviation of 2, like the second one. That way we don't have to do the square down here individually. That way it's more compact, you make less like calculation errors. Same thing, like this is also just the SE or the standard error for your confidence interval. So that is why right now it looks very complicated, but it makes sense. It's mostly just a lot of doing until you kind of memorize it. So let's go over a few examples. Alrighty, so I wrote down a example and I'm gonna use this example for both the standard deviation, the significance test, and for the confidence interval. So we have two classes that are being compared. In class 1 we have 10 students with a mean IQ score of 105 and a standard deviation of 10. And in class 2 we have 15 students with a mean IQ of 110 and a standard deviation of 10 as well. So let's first do the significance test. So what I always do when I am presented with a text is look at what is given to us. So what is given for our first class is that the mean was 105, their standard deviation was 10, and it was a class with 10 people. And in class 2, we have a mean score of 110, a standard deviation of also 10, and an n of 15. Now we have everything that we need. So let's look at our hypotheses, because that is very important. So our hypothesis, our null, would be that class 1 and class 2 have the same mean score. So the mu of 1 is the mu of 2. So they would say, like, actually the difference between class 1 and class 2 isn't there. They're the same population, they're generally the same. Versus the alternative hypothesis of saying, I think that mu 1 isn't mu 2. That is our hypothesis then. Well, now we're going to plug those in to our model. So we had x1 minus x2 divided by the square root of mu, like the significant, like the standard deviation squared, divided by n, and the standard deviation squared divided by n. So let's plug those in. That is 105 minus 110 divided by the square root of 10 squared divided by 10 plus, let's see, 10 squared divided by 15. We plug those in and we get a score of minus 1.224. And then we look at our table again. Well, we're at minus 1.2, so over here. And then we have another 2, so that's over here. Let's check that out. That is 1112. So our p-score is 0.11, what was it? 12. Well, if we compare that to our usual alpha of 0.05, it means that our alpha is smaller than our p-score. Our p-score is bigger than our alpha. Therefore, we fail to reject and we accept the null. That's it. We basically say that yes, there is very little difference between the two groups. Therefore, we accept that that the true population mean between the two is probably the same. They're probably from the same population. Now let's go into the confidence interval. Now we have our formula here, which is x1 minus x2 plus minus z times the square n1 plus square n2. Let's do this. We're going to plug it in, so that is 105 minus 110 plus minus, and we're going to give them a 95% confidence because it's always the same. It's almost always 95%. We can still see it's 196 times the standard error, which is 10 squared divided by 10 plus 10 squared divided by 15, which gives us 8.0016. So now it is 105 minus 110, 105 minus 110 minus plus 80016. 8016 is minus 13.0016 and 3.0016. So we can say with 95% confidence that the true population mean will, the true population difference will be between 13.0016 and 3.01. There we go. So, seeing as in this interval, there is a 0 in between those two, because if you go from here till here, there is a 0 in there, which means that there is a chance with that 95% confidence that there is no difference between these classes, which is of import, and it also correlates with our result when we did the significance test, where we said yes, there is no difference between these classes. The same thing with the confidence interval. If you know that the 0 falls in your confidence, your confidence interval, there is a chance that there is no difference between these classes. But that is the basics of the 2 sample. And I am also realizing that this video is going on for very, very long, so I think this might be a multi-parter. And then next time I record something, I'll go over the T procedure. So I hope this was helpful for some people. So yeah, bye bye.